Okay, we're going to get into our next unit, which is going to be on waves. Just some vocabulary really quickly for you. So wave is a repeating disturbance or movement that transfers energy through matter or space. Once again, there's different types of waves that we'll talk about, like obviously sound waves travel through the air molecules, like when I'm speaking right now. You can hear me because uh, airwave, the energy that's being carried through my voice is traveling through the air and reaching your eardrum. If there was no air in here, we'd all be dead. Good talk. But also, we wouldn't be able to talk either. And so if I was not able to, I could scream as loud as I want, but if there's no energy, if there's no matter to move my voice, doesn't matter. It wouldn't, I shouldn't say matter and matter in those words. Anyway, it's irrelevant because sound needs matter to travel through, but things like light doesn't. That's how light can reach us through space because it travels through the vacuum of emptiness where there is no matter present. So we'll talk about different types of that. When I refer to some of these terms of medium, medium is the matter in which travels. Waves travel through, like the medium which I'm speaking right now would be the air. That is carrying my voice. Waves can travel through the water. The medium there would be the water, etc. So medium. There's two different types of waves. I don't know how much I'm going to get into this, but there are transverse waves and compressional waves. Transverse waves kind of travel at the right angles. We'll talk about that when we talk about like electromagnetic waves. We'll get into that. A lot of these are just basic parts of waves. I don't want to get too much into this because I want to get, you should have already have a basic knowledge of this, but I want to get into more of the behavior of wave, which is what I'm more interested in. But other terms are going to pop up like wavelength, frequency, amplitude, especially wavelength, the distance between one point on a wave and a corresponding point on the wave. One point exactly like it, uh, just laid it down. So like it'd be like if I had like a wave that looked like this would be the wavelength from here to here, or from here to here. That's the wavelength, the two different parts of, from one part to a similar part on a wave. So that'll be like a transverse wave, which we'll talk about later. Frequency is the number of wavelengths that pass a point each second. And we're going to talk about this too, especially once again with electromagnetic waves. Like a long wavelength would look like this. I don't know why I'm using blue. Not my smartest decision there. Like, hey, blue background, let's use blue. Long wavelength would look like this. So if this took, let's say, 1 second from when I started to here, that's 1 second of time. 1 second of time. Well, that has a very long wavelength, but it would have a low frequency. I would have the frequency would be very small, whereas this, if I have a wave drawn like this, that would be something that has a short wavelength but a very high frequency, meaning that there are a lot of wavelengths that just took place, the number of wavelengths that pass a given point each second. All right, so a lot of times wavelength and frequency they're inversely related, where longer the wavelength, in this case, the shorter the smaller the frequency. And here you can see these don't have very long wavelengths from one spot to the other. Short wavelength, but a high frequency. All right, so frequency is the number of wavelengths that pass a point each second. And then amplitude would be, same thing, I'll take this awesome wave that I drew from where it would be at its rest position. All right, so I'm just going to draw a line right down the middle. The amplitude is how high up it goes, how high up the crest goes, which we'll talk about later. And you guys are probably familiar with this, like you hear amp. Like, man, dude's got a killer amp. Well, that's just because amp is the energy that's transferred by a wave. So the higher the amps, the higher the amplitude, the greater the energy. Now that's not always the case because with electromagnetic waves, that actually energy has to deal with frequency. We'll talk about that later, though. So. Waves are created by by the vibration of particles, and waves transfer energy from place to place. Now, this is important because a lot of times, when waves transfer energy without transporting matter itself. So energy can travel through. Think of like just think of like a boat when it moves up and down. It stays in relatively the same spot. A better example would be like the wave in a baseball stadium or in a football stadium. You stand up, everybody does the wave. It's like a pulse of energy goes through the stadium. You like wait your turn, you wait your turn, then you stand up and you throw your arms in the air, and then you sit right back down. So the wave travels throughout like once again, think of like a football stadium, soccer stadium, whatever you want to think of, where the fans do the wave. It goes through, everybody stands up, throws their arms in it, and they sit right back down. That pulse moves through the entire stadium, but the people themselves aren't getting up and moving and running around. They're staying where they're at. And that's kind of what a wave does. A wave transfers energy through it without the medium moving from place to place. Good times, those waves. A wave is a disturbance that travels through a medium from one location to another. Once again, I'm going to kind of cruise through this because I don't want to spend too much time on this. We're not going to worry about. I'll show you the example of compressional and transverse waves in class. And so, like, say you look at a wave like this, and you're like, well, the example I gave for wavelength would have been, like this. Like, oh, that's a wavelength from one point to another. Well, you look at this, that doesn't have a wavelength. What you would do is you would compare from one that's called a compression, where where everything's kind of bunched really close together, to another compression. It's to another compression. So you'd measure the distance from one compression to another, or a place where they're spread out, rarefaction, to another. So that's a compressional wave. Once again, I'll show you these in class. The amplitude of a compressional wave is how smashed together that is, as opposed to how high up it goes and how far down it goes, whatever. How dense. It says how dense the medium is, how tightly packed the medium is. So that was the worst underlining ever. How tightly packed the medium is. Energy, once again, energy is being transferred. If you do a compressional wave, I'll show this in class. I'll show this demonstration. Normally I do this in class, but we'll use a slinky. Slinkies are good to kind of simulate a wave because you can kind of see that the wave pulses through the slinky. The energy pulses through the slinky, but the coils themselves, as the energy passes, they go back to their original spot. So, and once again, waves are energy being moved through a medium with the medium traveling itself. So, sound waves or compressional waves are examples of compressional waves. When something is really loud, as opposed to, if I slam a book on the ground, or I slam a locker or something, what happens is those air molecules get slammed close together. They get compressed really tightly together, and that's what makes that kind of that loud noise, is how compressed they get. Again, I'm going to go over this in class. So sound requires, once again, I talked about this at the beginning, sound requires matter to travel through. Sound actually travels faster in solids and liquids than it does through the air. And if you think about that, because what do we know about, if sound needs a medium to travel through, what better medium to use than when the medium is really tight packed together? Because then if it transfers from one particle to another, well, in air it doesn't really travel that fast, because air molecules are more spread out, and so by the time energy gets passed from mine and then it collides with another air molecule and then another air molecule, it actually takes a long time for sound to travel through the air. But like a solid and a liquid, their particles are packed pretty tight together. And so when energy pulses through, when sound can pulse through a solid or a liquid, it can go by pretty quickly because energy is being passed from particle to particle. Well, in a solid and a liquid, those particles are really packed tightly together. And so sound actually travels faster through solids and liquids than it does through air. And this is how does soundproofing work then? Well, not all sound. We'll talk about and this is where I want to really get into the behavior of waves. Some material reflect waves, some absorb it, which that's what soundproofing material does. It absorbs the waves, the sound waves, and doesn't allow it to echo or reverberate off the walls or anything like that. It absorbs it. And so, but we'll talk about the different behavior of waves as well. And sound waves travel faster through warm air because the gas particles they're already moving faster. The air molecules are already moving faster. But if you think about, the old with sound waves, the lightning and the, jeez, I'm blanking here. Well, when you see the lightning and then you hear the thunder, because light obviously happens so fast. There's nothing faster than the speed of light. Uh, but sound, they tell you to count the number of seconds it takes to reach you, because sound travels about 330 meters per second through the air, and so by the time you see the lightning and then you hear the thunder, it takes about 5 seconds for a sound wave to travel a mile, and so that's where it gets. That's where that thing is, like, count how long it takes, and if it's however many seconds away you are, that's how many miles you are away. So anyway, uh, so sound waves can be transmitted. If you think like an ultrasound, when somebody's, it's not just for when you have a baby, but ultrasounds, they take place all the time when first doctors take a look inside you. What's happening there is the sound waves are creating an image on the inside. It passes through. Transmitted means it passes through. Sound waves can be reflected, and that's used, like the picture there is, with sonar. Sound waves get reflected. They bounce off of an object and they come back to the ship. And so during World War II, they were able to figure out the depth of these submarines, and if a submarine was there, by using sonar, they would send out a ping, and based on how quickly it came back, they could gauge roughly the depth of those submarines based on how it's reflected. And they can be absorbed, like I said, soundproofing walls, things like that. And we'll get into that. Transverse wave is what I talked about. A transverse wave, instead of the medium moving back and forth in the same direction, which is what happens on a compressional wave, here the medium will move up and down at right angles to the direction. So the wave is traveling this way, but the medium moves up and down. It moves at right angles to the direction that the wave is traveling. And a compressional wave, the medium is moving in the same direction as the wave. The medium and the wave are doing the same thing. And so, like, here's a good picture of the difference between, sometimes compressional waves are called longitudinal waves. So if you're like, what the heck's a longitudinal wave? That's what it is. So once again, here would be like an example of a wavelength of a compressional or longitudinal wave from here to here, whereas here would be an example of a wavelength on a transverse wave. But you can see the pulse is moving in the same direction. The energy is moving in the same direction as the wave itself. The wave's moving this way. The source, the coils are moving in this way. All right, whereas here, the source is moving like it shows up and down, but the wave, the energy, is traveling this way. All right, so those are the difference between the two types of waves. I might ask a brief question on that. I don't want to get too crazy on the different types of waves. I want to get more into the behavior of waves. And I did want to emphasize talking about like the different parts of a wave. So if I ask you to label the different parts of a wave, once again, and I will ask you this, like some of the stuff, some of these are terms that we'll have to know. Like this is a crest. A is a crest. Well, here, let me just go back. I'll just do this. This will be easier than me writing it out. So I could say like A and F are crests. My troughs, my low point of my graphs of a transverse wave, are D and I. So a trough is the low points, the crest is the high point, the trough is the low point. Amplitude would be like from the rest point from E to F, right there. That would be my amplitude. Amplitude can also go this way too. It's from the highest point on there. So from like where B is to A, that would be my amplitude. And then a wavelength, once again, any corresponding point. So I could say from B to G. And I'll make that green. I'll make it a different color. From B to G. That is a wavelength where the wave is going down and then the wave is going down there. That's a wavelength. So B to G would be a wavelength. I could say A to F was a wavelength. All right, as long as there's one corresponding point to another, there's a lot of examples you could use. All right, C and H, all right, whatever. Once again, some of the other terms I wanted to talk about, like frequency, number of wavelengths that pass each second. Period is the amount of time it takes for one wavelength to pass a point. I'm not going to talk about period as much, but frequency is going to be a term that you're going to have to know. Number of wavelengths, how, and it's just think about what's frequent. If something is frequent, it happens a lot. So frequency is how many times a wavelength happens every second. So a frequency is how many wavelengths occur per second. And like I said, they're inversely related. The frequency of a wave increases. As the frequency of a wave increases, the wavelength will decrease. All right, and I'm going to focus more on that than I will the other. We're not going to worry about calculating wave speed. I'm not going to worry about that. Not going to worry about that. Next video we'll talk about is the behavior of waves, which is what I actually want to get into. So.